NIMO is an open-source software package designed to accelerate autonomous materials discovery. NIMO provides a suite of algorithms optimized for selecting the next step from a discrete candidate pool. The candidate pool is prepared as a CSV file. By inputting the CSV file into NIMO, we can obtain the proposed next experiments, also as a CSV file. First, we prepare the candidate pool as a CSV file. The top row serves as the header. In this example, we have 3 experimental parameters and 1 objective function. All experimental conditions are listed here, with each row representing one specific set of conditions. Once experiments are completed, the resulting objective values are entered into the corresponding column. For experiments not yet performed, the column remains blank. NIMO then suggests the next experimental conditions from these blanks. This is the basic workflow for candidate pool preparation. Why does NIMO use discrete candidate pools? First, prior knowledge integration. We can embed domain insights directly into the search space. Second, flexible constraints. We can easily incorporate complex experimental rules, for example, ensuring the sum of 3 parameters equals 100. Third, guaranteed feasibility. No more impossible experiments proposed by AI period. Fourth, mixed variable support. NIMO handles numerical and categorical data simultaneously. For example, for this case, parameter 1 can be categorical while others are numerical. These features allow NIMO to handle a wide variety of exploration tasks. Based on the blank entries, NIMO selects the next experiments and generates a proposal's CSV file. NIMO features various decision-making algorithms, and depending on the one you choose, you will obtain different experimental proposals. These are examples of the decision-making algorithms implemented in NIMO. In materials science, research goals vary significantly depending on the project phase. The choice of algorithm should be tailored to your specific needs. First one is random exploration. When you are starting a completely new project with no prior data, random exploration is your first step. It helps you build an initial dataset without any bias, providing a baseline for more advanced optimization. Second one is FISBO. This is Bayesian optimization. Once you have some data and your goal is to find the best material, such as the highest conductivity or maximum strength, FISBO is the standard choice. It intelligently balances searching in unknown areas and exploiting known promising regions to reach the global optimum efficiently. Third one is blocks. If your goal is not just finding a single best point, but understanding the entire map of your property space, choose blocks. It focuses on exploring the diversity of materials, which is incredibly useful for discovering new chemical trends or identifying the limits of a material system. Fourth one is PDC, which is phase diagram construction. For researchers focusing on structural transitions, PDC is a specialized tool for mapping phase boundaries. It minimizes the number of experiments needed to draw accurate phase diagrams, saving you weeks of manual measurement. These are just a few examples. Our library is ever expanding to meet your research needs. Switching algorithms is incredibly easy. NIMO is a Python library, which you can install via pip install NIMO. The code requires only 2 main steps: importing NIMO and calling the NIMO selection function. In this function, you simply specify the algorithm name in the method argument. From here, you can seamlessly switch between FISBO, PDC, blocks, and more simply by name. You can also specify the number of objectives and the batch size. Once the code runs, it selects the next conditions from candidates CSV and outputs proposals CSV. Once proposals CSV is obtained, the next step is to acquire objective values based on those proposals. If you have robotic systems, integrating NIMO enables closed-loop exploration without human intervention. NIMO also fully supports manual experiments. By manually feeding back the objective values, you can still close the exploration loop. Simulation-based evaluation is another important strategy. Whether the objective function is acquired by robot, human, or computer, this feedback loop accelerates autonomous discovery. NIMO has already been implemented in several robotic systems. This is NARI, an electrochemical robotic system used for the automated exploration of novel electrolytes. Using NIMO with NARI, we successfully explored a vast parameter space for electrolytes. Compared to traditional grid search methods, NIMO achieved the same optimization results with only 10% of the usual experimental trials. This integration allows us to complete a month's worth of research in just a few days of autonomous operation. Next, we successfully created a closed-loop system for chemical synthesis using ChemSpeed, HPLC, and NIMO. In this study, we targeted the optimization of Suzuki-Miyaura reactions. The system explored a total of 192 different reaction conditions. This impressive dataset was built starting from just 4 initial conditions, followed by 47 iterative optimization cycles. A key advantage here is that the system enables continuous operation day and night without stopping. Even while researchers are away from the lab, NIMO and the robotic platform continue to propose, synthesize, and analyze samples throughout the night. This continuous high-throughput approach allowed us to find optimal reaction conditions far more rapidly than conventional manual methods. Furthermore, we successfully developed a human-in-the-loop system for composition spread thin film synthesis. This loop integrates NIMO selection with automated deposition, human-assisted sample transfer, and magnetic measurements. Using this closed loop, we optimized a complex quinary system and discovered new materials exhibiting high anomalous Hall resistivity. As shown here, NIMO is being implemented in many automated systems to support closed-loop exploration. Finally, the most important point. NIMO is open-source software under the MIT license. The website and GitHub page are listed here. NIMO is ready for you to use right now. So, now it's your turn to automate.